So we need to prove that this statement that we have is true by mathematical induction here, or by induction rather. So here, step number 1. So step number 1 is we have to show that the statement is true for n equal to 1. So what we do here is we get what we have this side. So we have n factorial equal to n+1 factorial minus 1 like this. Now, if we say 2 factorial, this simply means that this is 2 times 1. If we say 3 factorial, we multiply these 3 with the numbers before it, so we're going to have 3 times 2 times 1 like this. So this is what the meaning of this factorial means here. Now, we have to show that the statement is true for n equals to 1. So meaning that where there's 1 here, we substitute with the 1 there. So we have 1, open brackets, 1 factorial equal to 1 plus 1 factorial minus 1 here. So 1 factorial there is just 1. So 1 factorial is just 1 here. So 1 times 1 are going to get 1 equal to. Then this side here, we're going to have 2 factorial minus 1 here. Now, remember 2 factorial is just 2 times 1. So here, we're going to have 2. Oh, sorry. We have a 1 here equal to 2 times 1 minus 1. We have 1 here is equals to 2 minus 1. We have 1 equal to 1 here. So therefore, this is true for n equal to 1. Okay. So now we go to the second step here, which is the inductive hypothesis. So step number 2 is the inductive hypothesis here. Alright, under the inductive hypothesis here, we make an assumption that the statement that we have is true for n equals to k. So I mean that where there's n, we just substitute the k. So we have 1 factorial, 2 factorial here, 3 factorial, plus we have now where there's n, we substitute the k. So we're going to have k, open brackets, k factorial, plus, equal to what we have on the left hand side. It's going to be k plus 1 factorial minus 1 like this here. So under the inductive hypothesis, this is the only thing that we get to do there. Alright, so then we need to show that the statement is also true for the term which is the k plus 1 term here, so which is step number 3 here. So here we need to show that so we have to show that it's true for n equals to k plus 1. So here we have to show that it's true for n equals to k plus 1. So mean that here we have the k term there, so we need to show that it's also true for the k plus 1 term there. So mean that here we write the expression the way it is: 1 factorial, 2 factorial, 3 like this, 3 factorial, plus, then we have the k term. So before we get to k plus 1, there's n equals to k here. So I mean that we're going to include that term there, so which is the k term here, plus now, where there's n, we substitute with k, so we're going to have k plus 1, open brackets, k plus 1 factorial like this here. Like that there, equal to. So then on the right hand side as well, where there's n, we replace with k plus 1. So we're going to have k plus 1 factorial minus 1 here. Okay, so starting from the first term up to the k term, these terms gives us, or they give us rather, the left hand side of the inductive hypothesis there. So mean that we can just write the right hand side of the inductive hypothesis here, where there are these terms here. So we have k plus 1 factorial minus 1 plus this term here, which is k plus 1 and also k plus 1 factorial equal to k plus 2. 1 plus 1 are going to get a 2 factorial here minus 1 like this here. Alright, so I'm just going to rearrange what we have here so that we can look at it nicely here. So here I'm going to write k plus 1 factorial plus k plus 1 and also k plus 1 factorial here, then minus this one that we have here equal to k plus 2 factorial minus 1 like this here. Alright, now when you look at these first two terms that we have on the left hand side here, you'll notice that we have k plus 1 factorial and k plus 1 factorial that is common there. So meaning that we can just factor it out. We're going to have k plus 1 factorial, open brackets, here we're left with 1 plus, then this side we're just left with k plus 1 like this here, minus 1 equal to k plus 2 factorial minus 1 like this here. So now inside the brackets here we're going to have k plus 1 factorial here multiplied by, so 1 plus 1 are going to get a 2 here, so we have k plus 2 minus 1 equal to k plus 2 factorial minus 1 here. Now here this can just be written as k plus 2 k plus 1 factorial minus 1 equal to k plus 2 factorial minus 1 like this here. Now here, since we can just say since k plus 2 factorial here is just equal to k plus 1 multiplied by, so k plus 2 multiplied by k plus 1 like this here, meaning that where there's k plus 1 and k plus 2 plus k plus 1 factorial, we can just substitute with this here. So therefore we're going to have that k plus 2 factorial minus 1 is equal to what we have on the right hand side, which is k plus 2 factorial minus 1 like this here. So therefore what we have on the left hand side is equal to what we have on the right hand side here. So here we can just say therefore this is true for n equals to k plus 1. So if this is true for n equals to k plus 1, then the statement that we have holds under mathematical induction.